So now we're going to talk about triple integrals in spherical coordinates. And to do this, we need a volume element in spherical coordinates. So let me draw a picture, justify the equation for the volume element. So we have a theta and a d theta, and we have a rho and a d rho, and then we have a phi and a d phi. Move this row up. So that's our little volume element. Okay, so we got to figure out the dimensions of this little kind of stretched cube. So clearly this dimension here, the easiest dimension to figure out is d rho. That's one side of our cube. And then the other dimension is this green dimension here, which is shadows down here. That's going to be rho sine phi times d theta. Rho sine phi is this length here, it's r in cylindrical coordinates, and we multiply by d theta to get this arc length. So rho sine phi d theta is this little green length. And then last but not least, we have this, which is rho times d phi. Change in angle times radius gives us arc length. Put that together, we get our volume element. And if we shuffle things around so the d's are at the end, we get rho squared sine phi d rho d theta d phi. And that's our volume element in spherical coordinates. And just to be clear here, this length is rho sine phi, and this length is rho sine phi d theta. Okay, now we're ready to integrate. So let's move to an example. So we're asked to evaluate this triple integral over this sphere of radius 2. And in Cartesian coordinates, this would be a very difficult integral to do because you'd have to figure out the surfaces and the region in the xy plane. But in spherical coordinates, this is very straightforward. So the first thing we do is replace dv with our volume element, which is rho squared sine phi d rho d theta d phi. And then we put in our function in spherical coordinates. And if you look back at the change in coordinates, this is rho squared. It's the distance squared. And then we just put in our limits in terms of rho, theta, and phi. So rho goes between 0 and 2, that's the radius. Theta goes between 0 and 2 pi. And phi goes from 0 to pi. And notice that phi doesn't go from 0 to 2 pi. And the reason is if we go from 0 to 2 pi in the theta, we only need to go from 0 to pi in the phi to get the full sphere. And if we go from 0 to 2 pi, we'll be counting points twice. So this is our integral, and it splits nicely because it can be written as a product of functions of rho, theta, and phi. So we'll put the rho function first. It's rho to the fourth d rho. 0 to 2 pi d theta, and 0 to pi sine phi d phi. This becomes rho to the fifth over 5. Put 2 in that. This becomes just 2 pi. That's often what happens with the d theta integral. And this becomes negative cosine phi. And we're going to put pi and 0 into that. Pi into that is negative 1. So negative, negative 1. And 0 is 1. So it's minus, minus 1 again. So this is going to be 2. And this will be 32 divided by 5. And if we work that out, we'll get 4 times 32, which is 128 pi over 5. Let's move on to another example. So we want to find the volume of this spherical cone described by the set of points where rho is between 0 and 1, theta is between 0 and 2 pi, and phi is between 0 and some fixed phi, by computing the triple integral of 1 in spherical coordinates. So let me draw a picture of this region, and then we'll go about computing the triple integral. So phi is between 0 and some phi naught. Theta is between 0 and 2 pi, so that's all the way around. And rho is between 0 and 1, so we'll call this radius 1 here. And we get this cone like that. Okay, so that's our cone. And once again, this angle here is phi naught. That's a parameter. Okay, so the volume is the triple integral. Put in our limits here. So we'll have 0 to phi naught, 0 to 2 pi, 0 to 1. We'll have our volume element, rho squared sine phi, d rho, d theta, d phi. And then we'll have 1. Guess I didn't need to leave that much space as our function. Okay, so once again we split this. So we'll have 0 to phi naught, sine phi, d phi, 0 to 2 pi, d theta, and 0 to 1 rho squared, d rho. That's going to be rho cubed over 3 from 0 to 1. That'll be 1/3. This will be 2 pi, and this will be negative cosine of phi from 0 to phi naught. So we put phi naught in, we get negative cosine phi naught minus negative cosine of 0 times 2 pi times 1/3. If we clean this up, this will become positive 1 minus cosine phi naught times 2 pi over 3, which we'll put in front here. And a good thing to do here, we have this phi naught parameter, is to put in some phi naughts that make sense. So if we put in phi naught is 0, what kind of shape will we have? Well, if we put in phi naught 0, we'll have no volume at all because phi will go from 0 to 0. So we'll just have this little stick which has no volume. So that sort of checks out because if we put phi naught 0 in here, we'll get 1 minus 1, which gives us 0 volume. And if we put in phi naught of pi over 2, that should give us the half sphere. That should give us the volume of the half sphere. And if we put pi over 2 in, we'll get 0, so this will be 2 pi over 3. And that is half the sphere of radius 1. And then if we put in, let's put in something kind of interesting. Let's put in pi over 4. We'll get the volume of this cone, which is kind of like the cone I drew here. That's like 45 degrees. And that'll be 2 pi over 3 times 1 minus 1 over root 2. So apparently the volume of this ice cream cone shape is this strange expression. Okay, so that concludes our 22nd lecture. Have a good one.